What we're going to talk about today is something called acceleration due to gravity. So last class we glossed over a concept called acceleration, which means the rate of change of velocity, or how much velocity or speed changes over time. So we could define acceleration as the change in velocity over time. So if we were to put it as an equation, it would look like this. There's a final velocity minus an initial velocity over certain time. Every time that you have a final velocity that is different from the initial velocity of an object, there has to happen acceleration. So I have this marker here, and right now it's just staying right there. But if I let go, what happens? It falls. Here, when it was up here, it was at rest. That means that its initial velocity was 0 meters per second. But right before falling, right before it touched the ground, its velocity was not 0 anymore. Maybe it was, 20 meters per second. Let's say it was 20 meters per second. So since we have a change in speed, there has to have been an acceleration. And something that we're going to look at further in the year is that every acceleration has to be caused by a force. So what made the marker fall? Why, when I let go, why didn't it stay there just floating in midair? And the answer is something that you've probably heard about many times, that is called gravity. Gravity. So gravity is a force that pulls objects down to the center of the earth. And every object, no matter how heavy or how light it is going to feel this force pulling it towards the ground. That's the reason why we're standing on Earth and not floating around, and why everything tends to fall down. And gravity depends on how much mass there is pulling it to that object. So the more massive the Earth is, the more gravity there's going to be pulling us down, and how close we are from the center of the Earth. So if everyone and everything is basically at the same distance from the center of the Earth, and the mass of the Earth is constant, then that means that everyone and everything is going to feel the same acceleration due to gravity. So that acceleration that the marker felt when it was falling down is what we call, the title of this unit, acceleration due to gravity. So acceleration due to gravity. Due to gravity. And it's actually a very, very important number. So much so that it is given its own letter. So acceleration in general is written as an A. And every time you find an A in an equation, we're talking about acceleration. But if that acceleration is due to gravity, it has its own letter, G, small g. And it has its own value. So G is always equal to 9.8 meters per second squared. So remember, I told you last class that the unit of acceleration was meters per second squared, because it's meters per second, the unit of speed, per second, because it's the change in velocity over time, or per a certain amount of time. So this is a really important value that you guys should probably memorize, 9.8 meters per second squared, because it's everywhere. And what does that mean? It means that for every second, anything that you drop to the ground is going to accelerate 9.8 meters per second. Yeah, so it's going to go 9.8 meters per second faster. So if I drop an object at 0, after 1 second, its speed is going to be 9.8. After 2 seconds falling, its speed is going to be twice 9.8, which is 19.6, and like that. So every second, its speed will increase by 9.8 meters per second. That is what acceleration due to gravity is. So I'm saying this is a constant. That's not true for the whole universe. This is a constant for Earth. So this is the acceleration due to gravity on Earth. On the moon, you might imagine, the moon has less mass than Earth. And if you've seen videos of astronauts jumping around, when they jump, they can fly up a lot more and they fall slower. That's because there's less gravity on the moon, because the moon weighs less than Earth. So the acceleration due to gravity on the moon is actually around 1.6. So g is about 1.6 meters per second squared on the moon. And it also varies a little bit here on Earth. So the farther away you are from the center of the Earth, the less gravity there is. That means that here in Bogota in the mountains, the acceleration due to gravity is a little less. So here in Bogota, it's actually about 9.79 meters per second squared. And down at sea level, maybe in Cartagena, in Barranquilla, the acceleration due to gravity is closer to 9.81 meters per second squared. So it varies very little on Earth, but it does vary. But we will always use this value, 9.8 meters per second squared, to solve any problems or examples. Now what about in outer space? If you're far, far away from any planets, any moons, any suns, what is the acceleration due to gravity? 0. Because if you're not feeling gravity from any object, you won't fall. So there won't be any acceleration due to gravity. So in outer space, this value is 0 meters per second squared. The only one you really need to remember is 9.8 meters per second squared because it's useful for anything that's falling here on Earth. And there's a term to describe objects that are being acted upon only by gravity and that are falling down and not being stopped by anything. It's something you might have heard before. It's called free fall. Free fall. So free fall just means that an object that is being acted upon by gravity, so it's falling, but it isn't being stopped by anything. So it doesn't hit anything, it doesn't have a parachute, it's just falling because of gravity. So something about this might be sounding a little weird to you. So I'm saying that everything falls at the same rate. Everything falls at the same speed and accelerates the same amount when it's being thrown. But here, as an example, I have 2 pieces of paper, and one of them I'm going to crumble into a ball. So now I have 2 pieces of paper that have the same mass, but one of them looks like a ball and the other one looks like a plane. If I drop these 2, do you think they're going to fall at the same speed? Do you think they'll reach the ground at the same time? According to this, they should. But do they? Let's see. Definitely not. You couldn't see the ground, but the ball reached the ground much faster than the paper. So what was that? Am I lying to you, or what's going on here? So that is something that is called air resistance. Air resistance. So what happens is that there is air right now, and that's why we are alive, because there's an atmosphere that contains all of this air and this oxygen on Earth. And the air gets below the paper and it stops it from falling as fast. So the ball, if I hold them up here, the ball has a lot less air underneath it than the piece of paper. And every little bit of paper has a lot more molecules of air beneath it that is keeping it from falling. So of course, the ball is going to fall a lot faster than the plain piece of paper because it's going to be stopped less by air. So air resistance is the force that air makes that stops objects from going as quickly as they could be. Force of air that slows down objects. So here on Earth, it's really not common at all that an object is in free fall, because every single object that is falling on Earth is feeling some air resistance. So they're not going to be falling with an acceleration of 9.8 meters per second squared, but a little less that depends on how much air resistance affects it. So what affects air resistance? basically just the shape of the object. The shape of the object. So the more area of the object is being touched by the air, the slower it's going to go. And the more compact it is, the faster it's going to go. Many people, especially in the old ages, thought that mass affected how fast something fell. And they said, of course, if I throw a piece of paper and I throw a bowling ball at the same time, the bowling ball is going to hit the floor first because it's heavier. But actually, it had nothing to do with it. Mass has nothing to do with how fast objects fall. And Galileo Galilei, whom you've hopefully heard of, demonstrated this many years ago to prove to people that mass had nothing to do. So maybe you've heard about the Leaning Tower of Pisa. And Galileo got on the top of the Leaning Tower of Pisa and he decided to throw two balls. Two balls of exactly the same shape and exactly the same size, but one of them was made of wood and the other one was made of plastic. So one of them was a lot heavier than the other one, but they were exactly the same size and the same shape. So air resistance affects both exactly the same because their shape is the same, but if they fell at the same time, it would contradict the popular belief that mass had something to do with how fast objects fall. And that was exactly the case. They reached the ground at exactly the same time, proving, like Galileo had supposed, that mass has nothing to do. So many people still get confused about this because what we see in real life is that seemingly lighter objects fall slower than heavier objects, but that's not the case. It's just because of air resistance. So what would happen if we threw a feather and a hammer right here, a hammer, un martillo? The hammer, of course, would reach the ground first. But what if we did that experiment on the moon, where there is no atmosphere? So you've seen that astronauts on the moon have to wear their helmets because they can't breathe, because there's no air. So on the moon, there's no air resistance. So no air resistance on the moon. So that means that the experiment could be carried out even better than the one that Galileo did. And that's what astronauts did when they went to the moon. So actually, astronauts took to the moon a feather and a hammer, and an astronaut recorded himself letting go of the feather and letting go of the hammer at the same time, and they recorded how they reached the ground at exactly the same moment, because even though they have completely different weights and masses, they both accelerated at 1.6 meters per second squared, which was the acceleration due to gravity on the moon. So basically, if we were able to create a vacuum, vacío, with no air here on Earth, we would see the exact same thing happening. Both objects, or any object, would fall at exactly the same rate than on Earth.